This lecture, we are looking at molecular shapes and what's known as VSEPR. So we have been drawing Lewis structures, and this shows how atoms are connected in molecules and polyatomic ions. But Lewis structures are two-dimensional and molecules are three-dimensional. So knowing the 3D structure is absolutely critical for understanding molecules and their function. So for example, carbon dioxide, CO2, is a linear molecule, and we're going to draw this and look at this molecule here in a minute. But because it's linear, this means that carbon dioxide molecules are nonpolar and will not be very soluble in water, which is polar. Water molecules have a bent structure. This is one reason why water molecules are polar and have properties such as cohesion, surface tension, and hydrogen bonding. And knowing this helps scientists understand the shapes of more complex molecules like proteins and DNA, that's more than just 2 or 3 atoms bonded together. The shapes of these molecules play incredibly important roles in determining the jobs performed by these molecules in our bodies. So let's look at this atom. Atoms are surrounded by clouds of negatively charged electrons. And when you have atoms in a molecule together, these electron clouds repel each other. Because of this, a molecule will automatically adopt a particular geometry so that allows the atoms to be as far away from each other as possible. Think of these electrons as magnets of like charges. The closer you push them together, the more potential energy they have. And things want to be at the lowest energy possible. So if you let go, they'll push apart, lowering their energies, and atoms will do the same thing. And so if you think about this electron fields pushing away from each other, just like these atoms, we want to be at that low energy. So getting into molecular shapes, we follow this theory called VSEPR, valence shell electron pair repulsion. And a molecule can be described in terms of their electron pair geometry and molecular geometry. The electron pair geometry is what helps us figure out the molecular geometry. So the electron geometry is when we draw our Lewis dot structures and we can see all of those electron pairs around that central atom. That includes when we have two electrons that are next to each other, which is called a lone pair of electrons. And then when our molecular geometry is excluding those lone pairs because we wouldn't see them in the three-dimensional shape. But it is important to know that those lone pairs are there because there is a lot of repulsion that comes from that, and it helps us to determine those bond angles. So when we are looking at molecular shape, here are 4 important steps. Number one, write the Lewis structure, draw it out. Count the number of electron domains around the central atom, and I'm going to explain what that means here in just a second. So we need to count the domains. This is also called finding its steric number. That's going to help us to figure out our molecular geometry using a little cheat sheet here. And make sure, actually this probably shouldn't be number 4. This should be a little asterisk and go with number 2. But double and triple bonds count as one domain for determining molecular shape. So whether it's a single bond, a double bond, or a triple bond, however one atom is connected to another counts as one domain. Okay, so let's look at 2 domains, or a steric number of 2, or 2 things around a central atom. So again, a thing or a domain, or the steric number, is what is surrounding that central atom. So here I have BeCl2. And beryllium, if we look at the periodic table, has 2 electrons. So when we're drawing this, we might draw it like this. right? One electron on each side, Be. And then we're going to find chlorine, and chlorine has 7. 1, 2, 3, 4, 5, 6, 7. And we can see here that this will form a bond. And then we'll have another chlorine with 1, 2, 3, 4, 5, 6, 7. That will form a bond. So the way that we draw it, again, this does not tell us our shape, because right now I might look at this and go, oh, well, this is a bent shape. What this Lewis structure is going to help us see is that we're going to look at our beryllium. This is our central atom, and there are how many things surrounding Be? There's 1, 2. So it has 2 domains, or a steric number of 2. So flipping to our notes, we can look at electron groups, which tells us our steric number. If you want to write on above it, you can write domains, or you can write steric number. That's what this is referring to. So if I have 2 as a steric number, just like that BeCl2, if there are 1, 2 things around it, it's always going to be linear. Just like that BeCl2. Now, when we drew it with our dot diagram, it's okay that it was like this, but in real life, these electrons surrounding this atom and these electrons surrounding this atom will repel each other so much that it will form a linear compound. And that has a bond angle of 180 degrees. Now, there are other examples that I'm going to refer back to. On the slide, CO2 was another example, carbon dioxide. Now notice here's our carbon, and our carbon we know has 4 bonds. Right? So there are 4 bonds coming out of this carbon. It's a little disfigured now. But we know each oxygen has 2 bonds. So the 2 bonds from oxygen going to 2 of carbon. Carbon has 2 more. This is where the second will come from. And notice that I have 1, 2 things around that central carbon atom, steric number of 2. So it will be linear. So it's okay that there is 2 double bonds. Remember, single, double, triple bonds doesn't matter. We look at how many things or domains are around that central atom, and in this case it's 2. Another example that we're going to look at based off the previous slide was HCN. So again, here is carbon, my central atom. We know carbon can have 4 bonds. Here's 1 to the hydrogen, and we can see that there are 3 bonds going to the nitrogen. And again, there's 1, 2 things around that central carbon, and we can see that it is a linear compound. Linear as in they are all lined up. From here to here is 180 degrees. Now looking back at our slide, remember that CO2, that carbon dioxide example that we saw? Again, I wouldn't expect you to know that there was 2 double bonds in CO2. We would need to draw it out. Carbon has 4 valence electrons. Oxygen we know has 6. 1, 2, 3, 4, 5, 6. So I would look at this and go, all right, there's 1 bond, there's another bond. And CO2, we need a second oxygen because this carbon is not happy, right? So I might just put my oxygen here. 1, 2, 3, 4, 5, 6. We'll have a bond there and we'll have a bond there. Now, yes, it looks sloppy, but we can still see how many things are around this central carbon. 1 thing, 2 things. And we can see that each carbon has a double bond there and a double bond there. And because of there being the steric number of 2, 1, 2 things, it's going to be a linear compound. and 180-degree angle from this oxygen to the other oxygen. And same is true for HCN. Again, carbon's going to have 4 bonds. And nitrogen, if we look, nitrogen has 5, 2, 3, 4, 5. And let's see, the other one is hydrogen. Hydrogen has 1. So this one's easy. We can say that's fine and dandy. 1 bond. Now this guy, we can see that'll form a bond. This will form a bond. And while, yes, it is sloppy, but right here it will rearrange to form that bond. So we can see that this carbon, the central carbon, has a triple bond to nitrogen and a single bond to hydrogen right here. And because there are 1, 2 things around it, it is a linear compound. Let's look if there was 3 things around the central atom. For example, BF3. If I was drawing boron, we would know that it has 3 outermost electrons, and each fluorine has 7. Sorry for the sloppy dots. Fluorine has 7. 2, 3, 4, 5, 6, 7. So a bond there and a bond there, and another F up here. 1, 2, 3, 4, 5, 6, 7. So again, our electron dot diagram does not reflect its shape. Our electron diagram helps us to determine what the steric number is. And this allows us to see that there is 1, 2, 3 things around our fluorine. So it has a steric number of 3. Now with a steric number of 3, looking at 3 things around my central atom, we can see that its electron shape is trigonoplanar. Now notice that there are a couple different options within this 3 things around our central atom. In our case that we just looked at, the BF3, it's going to look like this. 1 boron with 3 atoms around it. We can see it as a trigonoplanar. It is all in one plane. All of these atoms are in one plane. What does this mean? The number of non-bonding electrons. This is how many lone pairs. Now, in this case, we don't have any lone pairs. We have our central atom and we have 3 atoms around it. So there are 0 lone pairs, which means not only is the electron geometry trigonoplanar, but our atom shape, our molecular geometry is also trigonoplanar. And it would look like this. And each of these bond angles is 120 degrees. Okay, so 120 degrees, 120 degrees, 120 degrees, which makes sense if it's in a plane that there's a circle that's fully 360 degrees. So 120 times 3. Let's look at that other example that's at the bottom of this screen here. We have our CH2O, and notice that there are still 3 things around carbon. Oxygen up here that has a double bond attached to it, and 2 hydrogens. So there are still 3 things. Its electron geometry is trigonoplanar, and notice that even though there is a double bond, just like we said, single bond, double bond, triple bond, all count as one steric number, one domain. So I can have, notice at the top here, 1, 2, 3 things around it. The only thing is, it's going to be a little bit different from my trigonoplanar example here, where they were all single bonds, and this one has a double bond. That's going to affect my angle a bit. Let's look at that. And if you think about it, my bond angle, if I have there's more density of electrons here with a double bond, right? There's more electrons here than there are here or here. And what do electrons want to do with one another? They want to repel, right? So what that's going to do is that's going to make this go, no, 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 we don't want these anywhere near us. It's going to push these guys down a bit. And we can see here in this slide, instead of 120 degrees, This actually will want to be 124.3, 124.3, which makes this angle down here a little bit smaller than 120. It's actually 111.4. These guys still want to repel each other. Don't get me wrong. They don't want to be closer together, but because there's so much density of electrons up here, they have no choice but to be a little bit closer to each other. It's still trigonal planar, but like I said, the angle is just a little bit smaller than the other example. Let's look at another example of three things around the central atom. So let's say we have this guy, three things around the central atom. But let's say, for example, SO2, sulfur, does not have, and notice that there are a set of lone electrons at the top of S. And if we were to draw sulfur out, I'm just going to put a plug here to kind of represent those lone electrons. If I were to draw sulfur, it has 5 outermost electrons. 1, 2, 3, 4, 5, 6 outermost electrons, just like oxygen. And notice that 2 want to be bonded to one oxygen, 1 to another, and it has the lone pair of electrons. So there are still 3 things around it. The oxygen, and those lone pairs. Those lone pairs count as one domain around it. So there are still 3 things. 1, 2, 3. Now, my electron geometry, if you look at our chart, says trigonal planar, but I don't have an atom here. We're going to pluck this guy off. There are still electrons here, electrons that are here that are repelling these other ones. So that's why it takes into effect how it affects the geometry. So now what shape do I have? I have a bent shape. Let's look at our cheat sheet. So while we're looking at this, again, when there are 3 things, 3 electron groups around it, our electron geometry, we said trigonal planar. Here's where we can look at the number of lone pairs. In that previous example, SO2, where S had 1 lone pair, that makes it a bent molecular geometry. And notice here, here's my central. I've got 1, 2, 3 things around it, but one of them is a lone pair. So it's like taking that trigonal planar and just popping one off. I still have electrons here. That's why it's pushing these 2 down. So I now have a bent structure. Now when it comes to bond angle, we said all of these were 120 degrees. What about this guy? So we plucked off the atom up here and we have lone pair electrons. Is it still going to be 120 degrees here? No, it's actually going to be slightly less than. Same idea. Here we have those lone pair electrons, lots of negativity up here. So it's going to push these a little bit closer to one another. So it will be just slightly less than 120 degrees. So those are our only 2 options for a steric number of 3. We can have 0 lone pairs, so 3 atoms, or 1 lone pair, so a central and then 2 others. Let's look at some examples with a steric number of 4. Here's an example of 4 things around the central atom. If I have methane, CH4, there are 1, 2, 3, 4 things around the central atom. Now they are all single bonds, and notice that it makes a tetrahedral shape. Let's look at our notes. Find the 4 things around the central atom. The electron geometry is tetrahedral. But if we look and see, there are 0 lone pairs around the central atom. So we would look at our notes, find the 0, and its molecular geometry is also a tetrahedral. 4 things around the central atom. Now these all are repelling each other, and the furthest they can get away from each other in this manner, each one of these bond angles is 109.5 degrees. 109.5 degrees from any way that you look at it. Let's look at another example here. I have NH3. Again, if I draw the electron dot diagram, nitrogen has 5 outermost electrons. So I'm going to draw 1, 2, 3, 4, 5, double up. So there is 1 spot when I had to double up those electrons. So that counts as a thing around my central atom. So I still have 1, 2, 3, 4 things around that central atom, which is going to be like this, but instead of an atom being here, there would be a lone pair. Now I have, and if you look at your notes, so I have 4 things around my central atom. So we're going to go down to a steric number of 4, but I have 1 lone pair of electrons. So find where the 1 lone pair of electrons, and it should tell you that it is trigonal pyramidal. Notice that it looks like a little pyramid here. All 3 of these guys, because remember the lone pair of electrons are up here, and they are repelling and pushing these atoms down. So what's going to happen to our bond angle here? These are going to be slightly less than 109.5 because those electrons are going to push these down just a little bit more. And we can see that here, that, yep, it's a little bit less than 109.5. It's actually 107. What's going to happen when I have 2 lone pairs? Let's look at water, for example. H2O, when I draw the electron dot diagram, water has 1, 2 lone pairs and 2 bonds. So a steric number of 4. Now I want you to look on your notes, find the steric number of 4, follow it over, and of those 4, 2 are lone pairs. Now we're going to take another one of these guys off. Lone pair here, lone pair here. So now I only have those 2 H's, and it is bent. Notice how it's a bent molecule? Now, again, still a steric number of 4. Its electron geometry, tetrahedral, 109.5 is that angle. This is going to be slightly less than when I had 1 lone pair because I have 2 lone pairs, so it's even more repulsive. And if we look down here, what did it tell us? With 2 lone pairs of electrons, yes, 109.5 would be the standard, but it's even less than when there was 1 lone pair at 107. This bond angle is about 105. Now we're not going to get into what happens when there's more than 4 things around the atom, but know that it can happen. If we were to look at 5 things around the atom, there's all sorts of different combinations. We could have no lone pairs, so 5 atoms around it, and we could see that that would form a trigonal bipyramidal shape. It gets a little bit more complex. I could have 4 things around, or 4 atoms around in 1 lone pair, and we can see the shape that it makes, and there's an example. 3 atoms around with 2 lone pairs, or 2 atoms around with 3 lone pairs. And then we can get into a steric number of 6, where I can have an octahedral shape with 6 atoms surrounding the central atom and no lone pairs. Or we can have 1 set of lone pairs or 2 sets of lone pairs. So lots of different shapes that can be formed. We're just going to focus on the 1, 2, 3, and 4 steric numbers. So let's do some practice here on our notes. This wants us to determine the steric number, classify the shape, and state the bond angle for each of the ball and stick structures. So here we can see that there is 1, 2 things surrounding that central atom. So the steric number is 2. 1, 2 things around this central atom. Steric number is also 2. Let's just go through and do all of the steric numbers, and then we'll go back. Here we can see that there's 1, 2, 3 things around this central atom, so the steric number is 3. Over here we can see that there is a lone pair of electrons, 1, 2, 3. Steric number is 3 on this guy. 1, 2, 3, 4 things. Steric number is 4. 1, 2, 3, 4. Steric number is 4. 1, 2, 3, 4. Steric number is 4 on this one as well. Let's classify the shape. So, looking back at my little cheat sheet here, everything with a steric number of 2 is linear and 180 degrees. So, doesn't matter that this is a triple bond and these are both single bonds. It's linear and 180 degrees. Now, We've got 2 with a steric number of 3. So let's look at our chart here. Steric number of 3. If there are no lone pairs, it's going to be trigonal planar and 120 degrees. So this guy was no lone pairs. So this is trigonal planar. 120 degrees. Now this steric number of 3 has 1 lone pair. So it's got 3 with 1 lone pair. So it's going to be bent. And because of those electrons, those lone pair electrons, it's going to be slightly less than 120 degrees. So we've got a bent structure, and it's going to be less than 120 degrees. Now we've got bunch with a steric number of 4. So we're moving down here. Steric number of 4. Again, remember, if there's no lone pairs, it's tetrahedral. 1 lone pair is trigonal pyramidal. 2 lone pairs is bent. So let's see here. 1, 2, 3, 4. This looks like a perfect tetrahedral. And it's going to be 109.5 degrees. Here I've got 4, but notice up here I've got a double bonds, double bonds. These 2 are single bonds. So it'll still be tetrahedral. But these double bonds are going to push our single bonds down. So we're going to say it's slightly less than 109.5 degrees. Because these double bonds here are going to push those other ones, make them smaller. And then here we've got 1 lone pair of electrons and 3 bonds. So 1 lone pair of electrons is going to give us that trigonal pyramidal. And it's going to be slightly less than 109.5. Okay, now why don't you pause the video here for a second and go back, look at the Lewis dot structures that we created in the lecture before this for these compounds, and let's determine the steric number, classify the shape, and look at the bond angle for each of the Lewis structures. So take a minute and then come back and we'll double check with one another. All right, let's look at number 1, which was CH3Cl. And we can see here that the steric number is 4, that it's a tetrahedral, and that it's a 109.5 degree angle. The second one, which was CH2Br2. So I've got my 2 H's, my 2 Brs all around carbon. So another steric number of 4. That's tetrahedral, 109.5. For number 3, which was CH4O, you'd be a little careful. If you were to just put your C with 4 H's around it, there would be no room for that O. So C, 3 H's around the C with an O around as the 4th spot, and then an H off of the O. So a steric number of 4, tetrahedral, 109.5. For this one, the CH2O, notice I've got my 4 around carbon, 2 are hydrogens, and a double bond to the oxygen. So we've got a steric number of 3. It's trigonal planar. And for our bond angle, we know that this massive amount of electrons in this double bond is going to push those hydrogens down lower. So this will be, this angle here and here will be greater than 120. And then down here is going to be less than 120. All right, the last 2, number 5, CO2, again, steric number of 2 because we have 2 things around that carbon. It's linear and 180 degrees. And then finally, NF3, steric number of 4 because those lone pairs count as 1. And then 3 F's, so 4, trigonal pyramidal, and that angle is going to be slightly less than 109.5 between those F's because that lone pair of electrons up there take up that space. Hopefully you're starting to feel pretty confident with this. Let's look real quick at these guys. These are just hypothetical compounds. We know that we would have a steric number. Let's do steric number down here. There's 1, 2, 3 for this one. This would have a steric number of 1, 2, 3, 4. This would have a steric number of 3. This would have a steric number of 1, 2, 3. This one would have a steric number of 4. This one would have a steric number of 2. This one would be 4. And that one would be 2. So using our cheat sheet here, let's look at our steric number of 3. And there are no lone pairs. So this is going to be trigonal planar. Trigonal planar here. This is a steric number of 4 with one lone pair. So 4 and 1. So it would be trigonal pyramidal. Steric number of 3 with no lone pairs. Another trigonal planar. So we've got 2 trigonal planars. The only difference between these two is that this one has a double bond, which, remember, that just means that my angles will just be a little bit different than this one. This one's going to be 120. This one's going to be slightly less than 120. All right, steric number of 3 here, but with one lone pair, so this is going to be bent. And here's the difference. We can see when we're drawing out our electron dot diagram, this looks like, hey, it's linear. But we got to be careful because it actually, in real life, would be bent. These lone pairs of electrons are going to be space hogs. So I'm going to have my Y's are going to be pushed down here. And then I will have a bent molecule. That's how our Lewis dot diagram or our Lewis geometry is different from molecular geometry. When drawn out, this looks like a linear compound, but we know in 3 dimensions, it's going to be bent. Here we've got 4 with no lone pairs, so this is a tetrahedral. 2 is going to be linear. 1, 2, 3, 4 with 2 lone pairs. 4 with 2 lone pairs is going to be bent. And then just 2 is going to be linear. Here's a website that is pretty helpful when trying to figure out what it actually looks like in 3 dimensions, just to give you more of a visual. So for example, if I have HCN, which was one of our first examples, I can just go, you can go right up to, this is called moleview.org. You can just type in HCN and the compound comes up and we can see that, oh, there's a triple bond to this nitrogen. So this is 1 steric number, and here's our second steric number. So 2 things around that central carbon. And then over here, we can move around and we can see that, oh, this is a linear molecule. We can move it around and see all the different sides of it. Another one, here was another one of our last examples, was NH3. So we can see that, now this is a little deceiving because this would appear that the steric number is 3 for NH3, but we know that nitrogen has a lone pair of electrons up here. So you got to be careful because if there are lone pairs, this doesn't show it, the electron aspect of it. So you might look at this and go, oh, it's trigonal planar. But when the compound is created, we can see that it's actually pyramidal, trigonal pyramidal. And it's like that because it has a steric number 4. There are those lone pair of electrons up here pushing those 3 down. So it is a steric number of 4. Another good one to look at, let's say we wanted to look at water. You can write in the common name for this compound as well. And it just comes up our H2O. So we can see that water is bent. H2O, it's a bent molecule. So again, this is just a nice tool to be able to see the 3D structure. Wouldn't count on it to give you the electrons, but in some cases we don't need to see them. However, it is important to recognize, oh, carbon has 4 bonds and 2 of them to this oxygen, 2 of them to this one, so there are no lone pair electrons on this guy. Steric number of 2, so it is a linear molecule.